So today our discussion topic is higher PCI injection, and it clearly higher means it is 100 and beyond, that is 130, 150 and 150, higher than 150 level. We are going to discuss two things. One is what is going to happen when we go for higher coal injection in the blast furnaces, and due to this increase in higher coal injection, what is the requirement of a cooling system and why? And technically, scientifically, we will calculate and see what exactly happen when we move beyond 100 to 150. So now coming to this second slide, which clearly shows, and all blast furnace operator know, when we increase PCI injection, coke layer thickness reduced, and this is what result into very high ore by coke ratio, and which subsequently produce high amount of hot metal, and this is how we increase the productivity in the blast furnace by increasing PCI injection. So once we go on a higher level of injection, coke has to remain for a longer period, result in coke breakages. And at the same time, when we increase our injection level, it's also forming a lot of unburnt char. So this both component actually reduce the raceway volume in terms of more fragmented particle which rest on the burnest base and making the volume smaller. Second result is that a lot of bosh gas rush towards the wall due to this effect also, and which result in increasing higher heat load of the wall. And at that time it's needed that the heat load sustained by the Bosch and Bailey region is to be dissipated by the cooling system, and here it require efficient cooling system. So now from here onward we will see, scientifically we will see that how much extra heat load I have to handle while burning once I go from 100 kg to 150 kg. So as in this slide is clearly visible that once we burn from 100 to 150 kg PCI, it's generate around 1600 megajoule extra, assuming our wanton coal almost generate around 22 to 25 megajoule. So all the heat energy is not dissipating on the wall, and assuming around 30 to 35% of heat which is sustained, which is felt by the side wall, is coming around 600 megajoule. So as we have clearly shown in our calculation that out of this 600 megajoule per ton, this translate to, which is equivalent to 800 kilowatt per meter square hitting the stave cooling system. But if you see the standard specification of a designer or the literatures available with the other plants, their cast iron staves only can handle around 400 to 500 kilowatt per meter square safely. At 150 PCI, the heat load exceeds this limit, as it is very clearly visible, and this is not desirable because as we know cast iron staves is much it has got a, if we compare the cast iron stave with the copper stave, then we can see that cast iron stave is 1/8 or 1/10 inefficient compared to copper staves in plotting the heat from the wall. As this slide shows that copper conduct heat 8 times better than cast iron, and as heat load increases and our property requirement goes it demand improvement. So at this level we need to dissipate, absorb heat from the combustion area and dissipating to the system quickly. And for these, as we have already shown, cast iron stave will not be very suitable. And once we try our effort to put the cast iron stave in handling higher coal injection, as we have shown that 150 level, which result in around 600 additional megajoule handling, and with its inferior conductivity and fatigue resistance property, it result into overheating of the surface, cracks and surface damage, loss of cooling efficiencies, and further it result in a serious failure. So it is already suggested that when we go beyond 100 and plus, in order to to handle this additional hit load, we need a copper staves which has got a properties much better compared to the copper, which result in extended lifespan, energy efficiency and cost saving also. And this is what the last slide summarize, that once we come with the copper coolers, it helps in taking care of deformation, weld cracking and wear resistance in a big way. Thank you.